Let's start with a real quick review. Before we deal with the measure that's given for angle 1, I just want to review some angle relationships. So starting from angle 1, we can determine that there is a specific angle relationship that exists between angle 1 and angle 9. Angle 1 and angle 9 are corresponding angles. They're in the same relative position to their individual parallel lines. At the same time, since line S and line T are parallel, angle 1 and angle 3 are corresponding angles. And so they would also be congruent. Now we can also look at angle 5 and angle 6. You should be able to determine that angle 5 and 6 are supplementary angles. Two angles whose sum adds up to 180 degrees, and we see that because there is the presence of a straight line. We could also look at angles 5 and 10. 5 and 10 are alternate interior angles. They are within the parallel lines, and they are on alternating sides of the transversal. So they are alternating interior angles. We could look at 2 and 13. 2 and 13, you should have guessed, are alternate exterior angles. They are outside the parallel lines, and they are on opposite sides of the transversal S. So they would be alternate exterior angles. We could also look at angles 8 and 12. Angles 8 and 12 are same side interior angles. They fall within the parallel lines L and M, and they are on the same side of the transversal T. Now remember that same side interior angles are supplementary, so the measures of angle 8 and angle 12 would add up to 180 degrees. Now with all of this information, we should be able to identify every angle on this image simply from knowing that angle 1 is 130 degrees. If angle 1 is 130 degrees, then angle 2 must be 50 degrees because angle 1 and 2 are supplementary. If angle 1 is 130 degrees, then angle 9 must also be 130 degrees because angle 1 and angle 9 are corresponding angles, and corresponding angles are congruent. If angle 9 is 130 degrees, then angle 6 must also be 130 degrees because angle 9 and angle 6 are alternate interior angles, and alternate interior angles are congruent. Now we also see that angle 6 and angle 8 are corresponding angles, so angle 6 and angle 8 would also be 130 degrees because corresponding angles are congruent. So hopefully you're starting to realize that having these definitions memorized and understanding the difference between congruency and supplementary is going to play a big role in your being able to solve for angle measures. Today I want to look at transformations, and then we're going to jump straight into one of those transformations called translations. Transformations, when the word is said, commonly brings up the idea of transformers. So now it would be appropriate to talk about what transformers do. Transformers change their shape. And so that kind of applies to what we talk about with transformations. With a transformation, there is a change that is taking place with the shape. We'll talk about that more specifically as we look at some of these examples. Geometric transformations. a change of position or size of a figure. The four types of transformations are translations, reflections, rotations, and dilations. Dilations we talked about earlier this year when we talked about scale factor. But we will do a brief lesson on it again as we are talking about transformations. Transformations are very common in geometry and in real-world items. And we'll talk about some of those as we progress through the PowerPoint. A rotation. A rotation turns a figure about a fixed point called the center of rotation. Now this year we will only do rotations around the origin, the point 0, 0 on a coordinate plane. An object and its rotation are the same shape and size. So if you are dealing with an image and it has changed shape or size, then you realize that more has taken place than just a rotation. So here we have an example of a rotation that has taken place, and this would be a 90-degree clockwise rotation. Again, we'll talk about that more specifically tomorrow when we deal with rotations. This is one example of a rotated image. It would be a good idea to go ahead and have it in your notes. Again, we will talk more about rotations when we talk about rotations and reflections tomorrow in class. Reflections. Everyone has a reflection. You stand in front of the mirror and you see the exact same shape and size of yourself as you're looking in the mirror. That's your reflection. A reflection flips a figure over in a line of reflection. An object and its reflection have the same shape and size, but the figures face in opposite directions. So notice that the word reflection, when flipped over this horizontal line, appears to be upside down. When dealing with a geometric shape on a coordinate plane, we will label each of the vertices, A, B, C, and D for this particular example. Its reflection will then be labeled A', B', C', and D'. Again, we saw this earlier this year when we dealt with scale factor, which relates directly to the transformation dilations. Dilations now. An object stretches or shrinks in size. And it stretches or shrinks in size based on the given scale factor. The original object and its dilation change in size using a scale factor. Now, hopefully you remember that a scale factor between 0 and 1 will cause an object to get smaller, while a scale factor that is greater than 1 will cause an object to grow. Translations. Within a translation, an object slides a fixed distance in a given direction without rotating or changing in size. The original object and its translation have the same shape and size, and they face in the same direction. Now, it is possible for an object to be both translated, which means that it moved a fixed distance, and then rotated. But that would be a compound transformation, and we're going to start with just doing basic transformations before we grow our understanding into compound transformations. So notice that translation simply shifted down. It didn't change in size. It didn't change in its shape. It simply shifted down and to the right each time. So we can think of polygon ABCDE as sliding 2 inches to the right and 1 inch down. And its new position will be labeled as A prime, B prime, C prime, D prime, and E prime. So again, a translation moves an object without changing its size or shape and without turning it or flipping it. Remember that translations are slides. A translation rule. A translation rule helps us to graph a translation on a coordinate plane, or at least understand how a figure is shifting on a coordinate plane. So an example of one rule would be xy forms x plus a, y plus b. Within this rule, xy is the original position of any point on our coordinate plane. Now it's important to remember that if we have a shape on the coordinate plane, depending on what shape it is, we will have multiple points. So if you have a triangle, you're going to have 3 vertices. Each vertice will have its own x and y value. The new position is determined by its shift, and we'll talk about that shift in just a minute. But first I want us to look at what's taking place there. The x and y is the coordinate for a beginning position on the original figure. The value of a moves an image to the left or right on the graph. And we notice that the value of a is attached to the value of our original position x value. And our x values, when we are graphing, are the values that move left and right on the axis. The value of b moves an image up or down on the graph. So y plus b will cause our image to move up or down on our graph. So here's an example. We have p, and p exists on our graph at the ordered pair 2, 2. We move to the right 2 from the origin and up 2 to get to that value on the graph. So I want to deal with the example, and we want to be able to translate p according to this given rule. xy forms x plus 3, y minus 2. So now we have a number in place of the a value, and it's connected with the x. So it is going to cause whatever my original value of x is to increase by 3. Or we can simply recognize that a x plus 3 will cause my ordered pair to shift 3 units to the right. Y minus 2 will cause my ordered pair to shift 2 units down. So we end up with p prime 3 units to the right and 2 units down from its original position. And we have performed a translation. Now, sometimes you're not given a coordinate plane. You're simply asked to translate p according to a given rule, and you're given an ordered pair. Well, if we were given the ordered pair 2, 2, as our x and y value, we could plug 2 in for x, and we would get 5. And if we plugged 2 in for y, we would end up with 2 minus 2 equals 0. So the ordered pair for our new position is 5, 0. And looking at the graph, we can confirm the ordered pair for p prime is in fact 5, 0. Now let's look at a shape on the coordinate plane. As I mentioned earlier, a shape is going to have more than one vertice and thus more than one ordered pair. Now, if we're graphing, all we need to remember is that x minus 1 causes my entire shape to move to the left one space. Y plus 5 causes my entire shape to move up 5 spaces. And so we're going to end up with a shape that has shifted in position, and P prime, I prime, E prime will look just like this on the coordinate plane. Now again, if we're not given a coordinate plane and we need to do this mathematically, then we simply plug in our values. P started at the ordered pairs 0, 5. So when I plug 0 in for x, I end up with 0 minus 1 equals negative 1. And when I plug 5 in for y, I end up with 5 plus 5 equals 10. So the ordered pair for P prime becomes negative 1, positive 10. I'm going to flip back to our graph for just a minute so that we can look at that. Our P prime is at negative 1, and if we counted all the way up the y-axis there, we would end up at 10 for the tip of our triangle. Our I original position is the value 2, 2. And so when we plug 2 in for x, we get 2 minus 1. Our new position x value becomes 1. When we plug 2 in for y, 2 plus 5 becomes 7. So the new ordered pair for I prime in the new position is 1, 7. And we do the same for E. The ordered pair started at negative 2, 2. So we plug a negative 2 in for x. Negative 2 minus 1 becomes negative 3. And we plug a positive 2 in for y. 2 plus 5 becomes 7. So our new position, E prime, our solution would be negative 3, 7. Now you should be able to practice on your classwork, and I will make sure that you have homework and key provided so that you can check your solution.